Hello, welcome to my talk on the calculation of the square root of a complex product. In this talk, I will first show you a very interesting example which seems correct in the calculation, but the result is incorrect. And then I will introduce the conventional expression for complex number and the complex number in modular argument form. And finally, the discussions on the real problem in the calculation. In mathematics, normally we have the calculation as this. The square root of a product A times B would equal to the square root A times the square root B. This is correct when A and B are real numbers. However, when it comes to complex numbers, this calculation could be wrong. For instance, if we have the expression as this, 1 equaling to square root of 1, and we can take the 1 in the square root as minus 1 times minus 1, and then according the above expression, we can have the expression as this, and then we can have the result as I times I equaling minus 1. Here, I is the imaginary unit. So we can see the calculation. We start from 1 and the result would be minus 1. So what the problem is in the calculation, or why the calculation is wrong? For a complex number, the most convenient expression can be expressed as this. The complex number A equaling to A1 plus IA2. Here, A1 is the real part of the complex number, and A2 is the imaginary part of the complex number. And if we want to calculate the square root of the product of two complex numbers, for instance, the complex numbers A given as this, B given as this. So the square root of these two complex numbers can express the product of complex numbers as this. If we put the complex in the complex plane, we could have the plot as this for the complex number A. This is very similar to the Cartesian coordinate. The real axis is x-axis and the imaginary axis would be y-axis, and A1 here and A2. And based on this, we can also have an expression for the complex number in a modular and argument form given as this. Here, R1 is the modular, the distance between the origin to the point, and theta 1 is the argument of the complex number. Sometimes we call this as the phase angle. And this modular and argument are given by this and this respectively. But for the complex number, its principal value would be decided by the argument theta 1 in a limit in this. So for a positive real number, because A2 would be 0, thus theta 1 would be 0. And for the same expression, a negative real number, the corresponding phase theta 1 would be pi. Here we'll have a look the square root of the complex number. So the first one we would see the square root of a product. In the calculation, we calculate the product first. So here we can see these two complex numbers a and b. If we times these two complex numbers together, we have the result for one complex number as this. And if we write the expression further, we should have the result as this. And then we would have a look of the product of the square root of the complex numbers. Here, square root of a times square root of b. So we have the expression as this and this. And then we can time this out. We have the result as this. So from this derivation, we should have the result as the square root of a times b equaling to the square root of a times the square root of b. But why this formulation can be incorrect when a and b are both complex numbers? We will see some examples in the next slide. So the results are calculated in MATLAB for the complex number a and b. So the expression of the square root of complex product, and this is the square root of a complex number times the square root of a complex number. We will see whether this relation would be correct. Here, there are three examples for different complex numbers a and b. The example 1, we can see the product first calculation. We have a result as this, and we could calculate the square root first and times these two complex together. So we have the result for the first example. These two methods give same result. And the second and the third examples, we can see these two different expressions would give different result. Compare this and this, this and this. Obviously, the first example is correct, and the second and the third examples are incorrect. Here, we must be noted in the calculation, the way calculating the square root by the product first is always correct, while the square root first might not be correct. In this slide, we will see what is the problem in the calculation. So we look at the square root of the product first, and we put this expression for a and b in modular and argument form. There would be no problem from here to there. However, we must be careful if we time these two complex together. The first case is when theta 1 plus theta 2 is larger than pi. In this case, the argument is not in the limit for the principal value for the complex, since theta 1 plus theta 2 is larger than pi. Then, in the calculation, we should minus 2 pi from theta 1 plus theta 2 to make it within the limit of the principal value. Therefore, the calculation would like this and this. The second scenario is theta 1 plus theta 2 is within the limit for the principal value. Then the calculation can be direct given as this. And the third scenario is when theta 1 plus theta 2 less than minus pi, which is not within the limit for the principal value. So to make it within the limit for the principal value, we need to add 2 pi into theta 1 plus theta 2 at this, and then the calculation would be at this and this. Here we have used e power of I pi equaling to e power of minus I pi. Both are minus 1, so we have the minus sign here. The calculation is in MATLAB. All this would be carried out automatically. We don't need to examine the case like this. But here I only make it clear where the problem is. And for the square root first, then we have the expression as this, and the calculation this and this. So we can see for the complex number, the square root of the product of A times B would be different from the product of square root of A times square root of B, since for different situations we may have different value. So in summary, we can have an expression for the square root of the complex product, and we have 2 different expressions when phi 1 plus phi 2 is within the limit of the principal value. Then we can calculate the square root first and then times them together. If theta 1 plus theta 2 is not within the limit of the principal value, we should have the expression for this. Here there is a minus sign, and we put the first situation as number 1 and the second scenario as number 2. We will see this difference in the following calculation. In this slide, we will look at some special cases. The first case is if A and B are both positive real numbers, then theta 1 and theta 2 would be both 0. Therefore, theta 1 plus theta 2 would be within the limit of the principal value. Therefore, we have the expression as the square root of A times B equaling to square root of A times square root of B. So this is satisfying the first condition. The example we can see square root of 1 can be expressed as square root 1 times 1 and then square root 1 times square root 1. So it is 1. This is correct. The second scenario is if A and B are both negative real numbers, then theta 1 and theta 2 are both pi. So we can see theta 1 plus theta 2 would be 2 pi. It's not within the limit for the principal value. Therefore, the expression of the square root of A times B would be minus square root A times square root B. This is the second scenario. So if we look at the example at this, square root of 1 would be equaling to square root of minus 1 times minus 1. And this would be minus square root minus 1 times square root minus 1. So it is minus I times I, and then we have 1. Therefore, we have the correct result here. The important thing here is the minus sign here. We can't simply take this square root as square root minus 1 times square root of minus 1. The third scenario is one of A and B is positive number and the other is negative. For instance, if A is a minus number, so we have theta 1 equaling pi and theta 2 is 0. Then theta 1 plus theta 2 would be within the limit for the principal value. Therefore, the expression square root of A times B would be given as this, the scenario 1. Now look at the expression. Square root of minus 1 would be expressed as square root of 1 times minus 1. And for the scenario 1, we should have the expression as square root 1 times square root minus 1. So equaling to 1 times I equaling to I. So this again is correct. Now we can use this principle to check the result we have seen before. The 3 examples. Here we also gave the argument theta 1 and theta 2 for the complex number A and B. For the first example, if we add the theta 1 and the theta 2 together, it is 90 degrees. So theta 1 plus theta 2 is within the limit for principal value. Therefore, these two calculations would be same as in the scenario 1. For the second example, added these two angles together, it would be 198.43 degrees. It is larger than pi. So theta 1 plus theta 2 is not within the limit for the principal value. So it should be the scenario 2. The result from the product first would be minus the value of the square root first. We compare this and this. Similarly, for the third example, theta 1 plus theta 2 would be minus 198.43 degrees. It is smaller than minus pi. Again, it's not within the limit for the principal value. Thus, it is the scenario 2. So we look at this result and this, we can see there is a difference of minus sign here. In the next 2 slides, we will look at the general situation for the nth root of the complex product A times B, whether it would be same as the nth root of A times the nth root of B when n is an integer larger than 1. We look at the product first. We can have the expression as this. And again, we have 3 different situations in here. The first situation is when theta 1 plus theta 2 is larger than pi, and the product of these two complex numbers would be given as this. The phase angle is subtracted by 2 pi to make the phase angle within the limit for the principal value. Therefore, we would have the expression for this situation. Note here this extra expression when theta 1 plus theta 2 is larger than pi. And the second scenario is when theta 1 plus theta 2 is within the limit for the principal value. And then we can directly calculate the nth root of the product. And the third situation is when theta 1 plus theta 2 is less than pi. So it is not within the limit for the principal value. Hence, we need to add 2 pi to the phase angle to make it within the limit for the principal value. and then the result would be given as this. So here you can see the extra term for different scenario. And if n equaling to 2, then this extra term would become -1, as we seen in the previous slide. And if we calculate the value by the nth square root first and time them together, so we have this expression and this. So again, we can see the both sides might not be same. It depends on the different situation, the phase angle. So if we put this together, we should have the expression for the nth root of the product of two complex numbers a and b. So it would be given in three different situations. When theta 1 plus theta 2 is larger than pi, it is given as this. And when theta 1 plus theta 2 is within the limit for principal value, so the calculation of the nth root of the product can be calculated as the nth root of the individual complex number. And when theta 1 plus theta 2 is less than pi, it would be given as this, so the extra term here